All right, looking at this integral, I've got to kind of go through my options. So I could try to use some sort of trig identity, but 1 plus sine to the fourth, I can do it as 1 plus sine squared squared and try to use trig identity there, but this doesn't look like a trig integral. I've got sines and cosines and then 1 plus sine, so it's not like sine to a power times cosine to a power with that 1 plus sine to the fourth in the bottom. It doesn't look like an integration by parts. Substitution is my next option. You could try to substitute for the entire denominator, but you can see the derivative is going to involve 4 sine cubed and then the derivative sine, so that's more than I need. I only have a sine and cosine in the numerator there, so that's not going to work if I do a substitution for the denominator. But the other substitution that we key on is when we can write the denominator as 1 plus something squared, so that it does turn out, if I do write this as sine squared squared, which is what I mentioned in a different context a minute ago, sine squared squared, sine x cosine x. This is of a form that if I substitute u for that, this is going to turn into an inverse trig functions integral. So because the derivative here is 2 times sine, and then the derivative sine is cosine, using the chain rule. And that's exactly what I have up there. Well, not exactly, I've got an extra 2. So that says that 1/2 du will replace that sine x cosine x dx. So that integral is going to become 1 plus u squared. That's, I just put the u in here, and then the sine x cosine x is going to get replaced by 1/2 du. I'm going to put the half out in front. This is in our list. This is tangent inverse. And just go back now to x, and our x is sine squared. So we've got 1/2 tangent inverse of sine squared. All right, on this one, well, this one sort of jumps out at you as looks like a integration by parts problem, and it is. In an integration by parts, if there's ever a tangent inverse in your integrand, you're either going to have to substitute in for it or use integration by parts. And when you use integration by parts, it's going to have to be the one that you end up differentiating. So it's tangent inverse of x squared. And then I'll just guess that I'm going to put the x over here as my part that I'm going to integrate, my dv part. Okay, so differentiating this tangent inverse, remember, you start with the tangent inverse. The derivative of that is 1 over 1 plus, and then it would normally just be x squared, but this time we have an inside function, so it's going to be x squared squared, and then the derivative of that inside function. Now that looks pretty messy, but it's not too bad because we were able to get rid of the tangent inverse completely. So we get something, it's not an inverse trig function anymore, at least. This becomes x squared over 2. Again, looks worse, but the fact that the tangent inverse is gone is really nice. So this is going to be x squared over 2 times tangent inverse of x squared. And then we've got minus the integral here. Well, that's going to be, the 2's are going to cancel. The x's are going to turn into x cubed, so I'm going to end up with minus the integral x cubed over 1 plus x to the fourth, because x squared squared is x to the fourth. And then I got to figure out how to do that integral, but hopefully you can see that's basically the derivative of x to the fourth. So I'm going to do that by letting u equal 1 plus x to the fourth, and du would be 4x cubed dx. That is 1/4 du will replace that x cubed dx. So I get x squared over 2 tangent inverse of x squared minus, so I'm putting 1/4, so I'm going to have 1 over u, that was what my substitution was for that denominator, and then my 1/4 du is going to replace the x cubed dx. So finishing up that integral, x squared over 2 tangent inverse of x squared. I've got minus 1/4 natural log u plus a constant. That is x squared over 2 tangent inverse x squared 1/4 natural log of 1 plus x to the 4th. And I don't need an absolute value on that because that's already positive. So that's my antiderivative in that case.